Good afternoon. Oops. Welcome to the last session of the day. Hopefully you guys had fun and learned a bit and networked a lot over the last couple of days. My name is Sri Ilaprolu, part of AWS public sector team. I head up our IoT practice worldwide, focused on public sector customers and partners. So what that means is working with customers, understanding their problem areas, working with partners in the ecosystem and the community to help build solutions that are cloud native and leveraging cloud services in general, so that customers are able to fulfill their missions. And being part of the public sector team, we're obviously focused on, we're more mission oriented and less so on features and benefits kinds of things that generally commercial sector tends to focus on. So in this session, we're going to take a little bit of a deviation from general IoT discussion, in that whenever you think about IoT, the first thing that most people think of are connected lights and blinky things and industrial IoT and all of this. Absolute great use cases, lots and lots of customer discussions and activity happening on AWS. There's nothing wrong in that. For this session, we thought we'll take a little bit of a different approach where we'll try to highlight a couple of stories, and we have two exciting customers here that will talk about what they're doing and how that's actually changing and helping communities around the world in dealing with problems that may not be the first thing that comes to mind when you think about IoT. So with that, I'm going to actually introduce Nitya to come up here from Nexleaf Analytics. Very exciting story, so stay tuned. Nitya?
Great, thanks so much, Sri, and thanks everybody for having us here. My name is Nitya Ramanathan, and I'm the CEO of Nexleaf Analytics. We are an IoT and data analytics company. We are a nonprofit, and we essentially work to bring sensor and data technologies to address some of the biggest public health and environmental challenges out there. So I'll share a little about what we've learned in deploying technologies at scale in a number of countries around the world. Our target countries are the 80 poorest countries. But first I want to take a quick step back and just talk about what are the broader trends and where are we going as a planet and a global economy. And for us, what we think a lot about are sort of where do the customers of tomorrow live? And it's really going to be in places like this. So we know that the Chinese middle class is growing quickly, and for example, in Asia Pacific, the middle class is going to be growing in the next decade or two by over 5x. And so as we think about how emerging markets are going to be driving the global economy, one of the things that we see is that it's really going to be important to start looking at not only the products that customers are buying, but also importantly the regulations that are being put in place in countries. And these will actually have tremendous impact on climate change, global poverty, and health. And why does this all matter? Well, we see a real opportunity. We've been around for about 10 years, and we've seen how spectacularly development solutions can fail. Fail when they don't think about who the customers are, what are the local contexts, and how you design for sustainability. So in order to give you an example, actually from my own life, I'll give you a little bit of how I kind of came to this work. So I started my PhD in computer science back in 2003, and this was actually where I did my thesis work, so Bangladesh. I got really lucky. My advisor was one of the early internet pioneers and had unlimited resources. So I got to define my own computer science challenges and problems, and I worked in what we now know as IoT. Back then it was called distributed sensor networks. And I wanted to understand why there was so much arsenic poisoning in the groundwater in Bangladesh. So I put out a bunch of sensors, got a bunch of data, wrote some great papers. And at the end, the women in the village were like, oh, we're so glad you're here. You're going to help us solve this problem. And I thought, oh, crap. No, I haven't done anything. I've written some papers. And so I then went and I raised $5,000 to help build a well in the village. And we all felt great. OK, we're going to help this one village at least get access to clean water. And I got on the plane back home, and I had my first realization. I thought, wait, who's going to fix this well when it breaks? Where are they going to go for a replacement part? How do I even know that this is the right well for this village? And I started asking myself all these questions that really to date, still very few people are asking about development sector innovations. So too often, when we think about affecting change in water and health, it's still this sort of charity mindset of handing out free stuff that doesn't have a long-term sort of sustainable model behind it. So when my co-founder, Martin Lukács, and I, who'd been doing our PhDs together, decided to start Nexleaf, the goal was really, okay, we see huge potential with sensors, but how do you bring sensor technology to both understand what the real challenges are and then actually define scalable, sustainable solutions that will continue to work in the long term? So we started Nexleaf Analytics. We build sensor, IoT, and data analytics technologies. We bring data to not only, as I said, understand problems, but actually take a market-shaping approach. So we look at the whole system. We look at how do you actually solve problems? How do you make big problems go away? So yes, we do sell sensor devices, but we also work with the WHO and the Gates Foundation and UNICEF to start asking what are the regulations that are needed. We work very closely with thousands of nurses on the ground to understand what they need. So I'll give you some examples of how we go about this, but I just want to sort of precede all of this by saying that we're very clear that data alone is not the answer. And one of the things that I love about working with AWS and with Sri, for example, is that he's really clear that cloud alone is not the answer, but that it can be part of a really crucial sort of bigger approach and longer term vision to solving big problems. And that's, I think, what we're all here to do. It's why we're at this public sector conference. So I'll give you a couple of examples from our work in terms of what we've been doing. But just to kind of summarize, for those who may not have context, as I mentioned, we do work in the 80 poorest countries. And what that tends to mean is that there are infrastructure gaps, things that we may take for granted here in terms of power availability, network connectivity, et cetera. And that local context becomes really important. 1.3 billion people in India alone, and such a diverse country. So really understanding the local dynamics and cultures and customs becomes very important in any product, in any solution that's deployed. Often the areas are remote, and we have to start getting creative about how we finance things for scale, because a lot of experimentation is needed, a lot of patient capital is needed. And finally, maintenance is a really big issue. So really thinking about how do you put in place properly incentivized maintenance models to ensure that whatever solution's being developed is going to sustain. So these are some of the principles, you could say, that we think about as we scale interventions. So the first example I'll talk about is vaccines. Vaccination is actually one of the most cost-effective public health interventions out there, period. And one of the challenges, though, is that most vaccines actually have to be kept cold. So if they get too hot, or surprisingly for some vaccines, too cold, they will lose their efficacy. And so a mother will think that her child is protected, but they're not. So the challenge is really that vaccines are kept cold through refrigeration, and that very often, either because a power goes out or a refrigerator fails, the vaccine's exposed to bad temperatures. So a clinic like this one, for example, may have an old refrigerator that doesn't work all the time. The truck that delivers vaccines to this clinic may have an old refrigerator that doesn't work all the time. So how do we start helping countries make smarter, better decisions about how to manage their vaccine cold chain? Well, we worked with Intel to build an IoT device. And it's a small black device, looks kind of like a router. You see it in the back. And it monitors temperature, sends it out over the network, no rocket science. Sends out a text message to nurses when there's a problem. And we started to kind of think about layers and layers upon layers. So this was in Kenya. And so we started working in one district with about 50 clinics in Kilifi district. And we started saying, OK, let's send a text message to a nurse. And let's ask the nurse, what are your pain points? What are you trying to do? How do we help you do it better? And so we started crafting the alerts, the types of information, the data to answer her or his key questions that they were struggling with. And then we said, OK, you're able to solve some of the problems, but not all of them. We actually did a randomized controlled trial in Mozambique. We found that when fridges call for help and you give nurses this type of information, you can get a dramatic improvement in the vaccine cold chain, because there's quite a bit that nurses can do. But we still weren't getting all the way there. We're still seeing failures in the cold chain. So, we started working with district officers and with technicians. We started saying, okay, well, what are your big questions? How come the technician doesn't come out when the nurse calls? Okay, it turned out that the technician didn't have the spare parts. They didn't know what type of failure it was. They weren't able to plan because they didn't know what were the most common failures. So we said, okay, great, we're gonna start crunching the data and help you answer those questions. So we did that. We helped technicians remotely diagnose problems when they came up. Clearly not getting a hang of the clicker, sorry. And then we started looking at, okay, beyond that, why is the maintenance technician not getting the funding they need in order to actually come and visit the clinic whenever they need to? So then we started working with the government and figuring out how does the government actually allocate budget for maintenance technicians? And we started doing this in a bunch of countries. And as we did this, we started finding some patterns, some common problems, some common questions. And so probably our biggest scale was in India. The Ministry of Health in India heard about our work. We helped the government do a pilot. And then they decided to put out an RFP, went through a whole multi-year competitive process. And we actually ended up winning that bid to sell the government 15,000 devices. So we then we were the lucky winners of the contract to go around and train thousands of nurses across the country to install these devices, train nurses. And so our technology is in about 14,000 clinics now, which covers about half the birth cohort receiving vaccines across India. So massive scale. We're talking about approximately 12 million or more babies a year that receive vaccines that are now protected with the ColdTrace technology. So we're really excited about that potential scale, but there's so much more to be done. But what we've sort of figured out now is what are the solutions that are needed and how do you help governments start to answer and deal with some of the key questions that they have with better data, along with better training and resource mobilization. And so, we really started with the clinic, with the nurses, answered their questions, built our way up. And what we found is that when we stepped back and we took sort of a global look, actually at the global vaccine cold chain, and now when I say global, I'm talking 80 poorest countries, we found that not only are the challenges in the country, but actually the feedback loops that we were able to provide were really beneficial for some of the other market players. So fridge manufacturers, if you're a fridge manufacturer and you're selling fridges in the 80 poorest countries, you don't have a very big markup. You're doing this not out of charity, but because you think it's the right thing to do. That's awesome. But the way that the current market works, fridge manufacturers get no feedback on their fridges and how they're working. They just get a lot of blame and pointed fingers when they don't fulfill a warranty. So we started working with fridge manufacturers to say, hey, how can we give you post-market surveillance information that you want? So now you're incentivized to participate in this market and make better products that nurses want. We started working with the World Health Organization that develops out the standards for all these technologies, whether it's fridges or temperature monitoring. We helped them actually start the market for remote temperature monitoring in clinics by developing a set of standards. So I'm so sorry, I'm gonna grab something to drink. Oh. And so what we were trying to do through building out these standards was actually build a healthy market so that other manufacturers could come in, other providers, but that they would be coming into a market that was a little bit more rational. We started working with countries to help them think about data privacy and data policy. So really sort of taking a very holistic approach to everything. So I'm going to talk a little more briefly now about one other use case that we work in climate change. And then I'll talk a little bit about the technology solution. So the other area that we work in is in climate change, specifically looking at how the poorest 3 billion people, roughly half the world's population, cooks. So cooking, it turns out, is one of the most basic things that all of us do. But about half the world's population actually cooks using pretty sort of prehistoric methods of burning dung and wood over fires. And this produces a lot of smoke, actually leads to the deaths of close to 4 million people every year. This is more than the number of people that die from HIV, malaria, and TB combined. Really massive health issue. And the solution is to design better combusting cook stoves, like the one that you see on the right. But the development sector has been looking at building better, cleaner cook stoves for the last roughly 50 years. And when we started putting sensors on cook stoves, just to start asking, let's just see what's working, what's not working, we found that across the board, nobody was using the clean stove. And so you had all these big, fancy studies coming out of all these universities saying, we're not seeing any impacts. We don't know why, that people's health aren't getting better. And we were kind of like, I think it's because nobody's using the stove. And so we, through putting sensors on stoves, started doing the exact same thing that we had done in the vaccine cold chain. We started asking women, what are your pain points? And when you first ask somebody, how's their cooking going, you, me, everybody will give you a generic answer. Oh yeah, it's fine, it's great, I don't know, I cooked about 5 hours this week. And what we would do is we would actually show them the dashboard. I don't have a picture of it here. But we'd say, oh, that's so funny, because actually if you look at the dashboard, you can see that you were cooking on the clean stove for 3 months, but you actually stopped using it. What happened? And then you get the real story. Oh, well, the stove broke, or, my sister-in-law was using it, but now that I started using it, it's too short for me. You get all this sort of actual information on why people continue to use stoves or not. And so going back to sort of what I said, it's not just about the data, it's certainly not just about sensors, but we need really sort of a lot of different ways of really understanding what do end users need, and how do we kind of build solutions that will help get them that. So we started kind of understanding what stove manufacturers needed, what the last mile service technician needed, what did the financiers need, and really, again, took sort of this market shaping approach in clean cook stoves to really start understanding how do we design better stoves, cleaner stoves that women love, so that they switch over to using something, and then they can call somebody when the stove breaks, just like you and I can when our stove breaks. And so it's been a work in progress, and one other thing I'll mention is, so this is a slightly old picture, but we have a sensor device on the wall. Now it's much smaller, just fits directly on the stove. But this sensor monitors usage of the traditional and the improved stove, sends the data to a back-end cloud. And one of the things that we found was that because affordability of these clean stoves was such a challenge for households earning less than $2 a day, we started helping women get connected with essentially climate credits. So much like a big coal company gets a whole lot of carbon-based payments for switching over to a cleaner process, we said, why can't women get that same thing? So we helped women start getting small payments every time they use the clean stove. And this is helping women now pay a service technician to actually come fix the stove when it breaks, to pay off the loan for the stove, things like that. So a couple dollars a month. And so essentially, this is what our system looks like. All of our data goes to AWS. And this is what our system's been looking like for some years now. And one of the things that we're really excited about is as we start growing, right now we're just at a couple thousand clinics, less than 1,000 women on the clean cooking technology, but we have a lot of growth coming through our partnerships with the Gates Foundation, Gavi, et cetera. And so we're looking to scale to about 100,000 devices roughly by 2020. And so as that growth comes, while my co-founder and I, we have a great engineering team, still being able to design for that kind of scale quickly, and also for modularity so that it can work across lots of different types of information system networks, because data flow, flexible, easy data flow and analysis is critical. And also not only modularity, but being able to design so that when we do need machine learning, we do need AI, we're ready for that. We're already seeing the use cases emerge. So really kind of thinking about that next generation architecture is one of the things that we've started working with the AWS team to essentially do a scalability audit, a security audit, and a scalability audit. Sorry, and a machine learning audit. So that's been really fantastic for us. Oops. So I think in the interest of time, I'll probably just skip this slide. One thing I'll mention briefly is that as we kind of design constantly for women, we've seen a lot of opportunities to not only think about new solutions, but also think about new partnerships that are going to help build this market to solve global health challenges. So you can't exactly see it in this picture, but with Intel, we actually designed a bangle that women would wear that would actually alert them to their exposure to smoke. And so this is just one of the examples of technologies that we're thinking through, much more early stage, early pipeline. But as we think about new innovations, just kind of bringing that same framework to bear. So at Nexleaf Analytics, we're really proud of the sort of scale and the impact that we've been able to have, not only improving vaccine cold chains, but also reducing air pollution and women's exposure to smoke. So I'll just kind of conclude by talking about, sort of our approach. So as I mentioned, we're very bottom up. We're really customer driven. And we've had great opportunities to work with the World Bank and the development sector, some big organizations that can deploy solutions at scale. And what we've found through this is that it's the partnerships that have been so important as we think about how do you help countries think through new data regulation? How do you work with telecoms to actually scale out IoT infrastructure in clinics where maybe the cell phone network isn't so strong? How do you design new back-end scalable data platforms? We found that the partnerships are so crucial to helping us work towards the 11 Sustainable Development Goals that we've been working towards. And so we're really excited to be here, having these conversations, really thinking about how academics, philanthropists, private sector, governments, public sector can really work together to design the types of solutions that are needed to meet the sort of dynamic markets of the future that we see coming. So thank you so much.
That was a great project. And the vision also for a broad spectrum of the world about helping people. So Storm Sense, this is a project we had been working on for the last 2 years. And let me go back. I think, so I'm a systems analyst at the city of Virginia Beach, and my background is in civil and geological engineering. And I've been doing geospatial technologies for like 15, 20 years. And I have Dr. Loftus, John Derek Loftus, and he's a research scientist at Virginia Institute of Marine Science. And city of Newport News, Virginia Beach, and also Newport News, Virginia Beach, we all are partners in this project. And what we started off doing is here, I'm just giving you a summary here. Our important part was to proactively do addressing the flooding problems. And we are in a place where on the East Coast, our population is around 30,000, and we have 10 cities around, and that 10 cities combined are called Hampton Roads region. And we have the Eastern Naval Fleet there resident. And also we have hurricanes sometimes milder and sometimes major, and also we have sea level rise to deal with. So we started off our partnerships, like our funding came from NIST, National Institute of Standards and Technology, and also our partnerships and all. We started as a Global Cities Team Challenge was a project we started off like a Shark Tank pitch, and then from that we got some money from that. And then we started our journey on AWS Cloud, and that was due to one of the important things we need to cover was replicability, and we thought that cloud is a better replicable way of doing our project. So here, this is the problem, and the problem mainly is for flooding is communication and messaging. And a lot of times you have different hurricanes, and what happens is the next day you open the newspaper, citizens will say, oh, I didn't know that the flood insurance was so low. Like, it's like $400 per year is the flood insurance from FEMA most of the time for like $200,000 off your property, and then $80,000 for the contents they cover. And people say that we don't know. So we want to increase that awareness through our project, as well as through modeling, and as well as to give the data into their hands as soon as the data is up there. So that's our main challenge, and we are trying to use that awareness as our pitch. And over a period of 2 years, we are hoping to gain a lot of understanding for them too. So here is like a little fast way of looking at. So in 2013, we reviewed and current implementations in research and in sensors as well as the flood modeling. And here what we did was, in 2013, we brought the university to the city, and we did some research on the outside, what is happening in the flood modeling. Then we went through that process and then selected few of the sensors there. And also in July 15th, we started another project in the city itself and brought the 10 US Geological Survey sensors and installed in our city. And then before that, we didn't have any sensors except 4 NOVA sensors. And then after that, we won the Replicable Smart City Technologies funding from NIST, and we participated in that challenge. After that, we installed our first sensor in Newport News in June 2017. And then what we did was, after that, we also used this project, and through the prototyping on AWS, we brought this into, in 2017, we won the AWS City on a Cloud Challenge through this process also. So additionally, we are added 16, 17 sensors after that, and now we are going to add additional 23 sensors by end of 2018. So this is our prospective partners, all the regional cities in the Hampton Roads. And on the left side, you see US Ignite, NIST, and Global City Teams Challenge. Global City Teams Challenge, you can all join. If you're a city or any other organization or private company, you can join that, and it's still running. So that's a good way of putting your projects in there and then competing there and then getting funded sometimes. And this is our team here. Front is NIST program manager, Dr. Sakwu Ree, and he's the Cyber Physical Systems Assistant Director. And these are the different sensors we were using, and one is we were testing some of these sensors in this prototyping. This is a street corner sensor, so we used one of these prototypes. And then, so this sensor is going to like record the street flooding. And then we use that sensor data here to do some of the calibration, the tidal calibration of the sensor. There is a program called Tide Watch in Virginia Institute of Marine Science. They can give us, using our sensors, they can give us 30-day prediction of the tides, what is going to happen. So there are like 4 different options. We can figure out 3 days, 7 days, and 30 days. So we tested that sensor for that calibration. And NIST, our guidelines from NIST is we have to test and we have to produce papers in journals. That's what we did in this project as well. So we recently closed the project, and we have couple of journal papers out there. So this is the sensor proliferation. This is in Virginia Beach and Newport News. We added 10 sensors currently in Virginia Beach, and you are seeing here in the left bottom corner, there's a picture with our sensor as well as the USGS sensor, both close together, and that's for calibration. We are using USGS sensor data as a calibration for our sensors. And you can see also the different structures we had to put on. So there are bridges, most of them are bridges, and some are concrete abutments, and some are railings. So, and some of these are temporary sensors we are putting. So 4 sensors are temporary in coordination with the USGS locations, co-locating those sensors so that we can do a 3 or 6 month period of calibration before we remove the sensor and put it in another place. So deployment lessons. So when we deployed, 2 days later, all the sensors went down. So so that was a field test. So what we did was we had to go through the box and then change the different configurations so that the sensor blocks, the whole box sleeps 5 minutes, wakes up 1 minute, sends the data. So all the data is every 6-minute interval. And then we had to make sure for the timer and data frequency, we wanted to make sure that it corresponds with the NOAA and USGS frequency so that we can do the modeling in the university so that all the data comes in 0, 6-minute, 12-minute intervals from our sensors, from NOAA sensors, and USGS sensors. So that's how the data frequency happened. And our installation, we used one city used their city employees, and we used contractor. and we were looking at the cost differences. All that was published in that papers. And then we were looking at data spikes. What happens is you have like sudden random data spikes within a 6-minute interval. So we are putting some algorithms to reduce that spike so that it flattens out that curve. And the range, sometimes your sensor comes with a default range, and you have to reset the range such that depending on the height between the bridge and the water level, you can differentiate the height, and then you can adjust the height in the sensor. So the sensors are very sensitive, so you do that. All these sensors are ultrasonic, and some are radar. So we use like few of the radar in one city, and we have a lot of ultrasonics in our city. And there are two manufacturers. One is Valarm, and the other one is Scenics. Valarm is the box provider, and Scenics is a sensor. And there is another sensor manufacturer is Flowline, and we are using most of the Scenic sensors now. And Scenic sensors are also being used in Iowa, state of Iowa. They have 150 sensors, and on the Philippines island, there are like 1,000 sensors. So we did all that research before we chose the sensors as well. And the Scenic sensor was sent out to USGS for them to calibrate with that, and they were like 0.01 feet difference between those two sensors. So this is the predictive tidal calibration tide watch network. So this network is providing the NOVA sensors, and then these are our sensors. You're seeing the projected water flow which will happen over a period of time, and these are the predictions it's making there. So this is the area. So this is the hydrodynamic modeling which Virginia Institute of Marine Science is doing, and they use LiDAR data, and they do it at 5-meter level, and that's almost equal to the street level flooding. You can start looking. So when you look at this, you see the spreading of water, and all this is done through their modeling process. And it considers flooding. It also considers the wind, rain, and storm surge in these scenarios. So all this comes through Esri platform for ArcGIS Online we use for getting the data. All the real-time data comes as well through that process. So in the future, we can predict better in these type of scenarios about flooding. And here, also we wanted to make sure citizens are involved in it. So this is where we did one on November 5th, 2017. That's the highest tide. Every year, one day is the highest tide, and they call that is the Catch the King. So we have an app. That app was used to collect data. And then what you see here is 510 participants around the Hampton Roads, 10 cities, 600 volunteers were there. All are citizens. They came, and we pre-drew that November 5th outline of the water which might happen through modeling, and that was calibrated. So what citizens did is they used the app and then clicked along the water line dots and in GPS. So with that, we collected those. Those were the 53,000 points they collected in a single day on a Sunday. That was a good thing. So that, and then how we made the citizens come over to this whole project was through Catch the King. It came on NPR and everywhere within the region, and a lot of newspapers. So that's how we brought the volunteers into picture to do citizen science for us to calibrate our models in the future as well. So every year they'll be repeatedly doing that. So here the journey begins, and with AWS. So replicable smart cities technologies is the definition that was given to us by NIST, and how can you replicate this around the world or around the US, and can you do that way? So in regionally, cities will think as city way of installing the infrastructure within the city and then trying to develop. We said that's not the way we can do it. We can only do it through cloud. And then what happened is, when you get Christmas vacation, you have few days, what do? You jump on your Google account, and I went on to AWS and spun up a server, and then that became a prototype for the Scope conference. So that's where we presented in Scope conference our thinking, and then we used that concept. Also, NIST has introduced us to AWS team. Sri was introduced to us there. And then we also pitched our project into the City on a Cloud challenge, and that's how we got the $50,000 awards to jumpstart our project through the cloud for the replicable smart cities. So this is the initial prototype. We came up with this storm sense, and on the left side you see all the federal agencies data and the local communities data and the cities data coming. And then you have precipitation data from, so the cities have public works and public utilities, and they have their own precipitation data behind their firewalls. So we are trying to getting all that information through. And initially we started with MeanStack and Node.js and MongoDB, and then we switched to AWS after our challenge win, and through that process we switched to DynamoDB. And here also our formats, so that the data which comes out of that stack has gone through, and then it goes to the mapping and charting. So this is the emerging ideas and architecture. So this is the current architecture we have, and this is the running architecture. So on the left side you see all the different lambdas working on the sensor data from multi-clouds. So when I'm talking about multi-clouds, USGS has their own cloud, our sensors have our own cloud, NOVA has their own cloud. So you're bringing all that cloud data into in real time. So every 3 minutes, 5 minutes, the lambdas are working, bringing that data. And then here what we do is we put a CSV JSON in an S3 bucket, and that is connected directly into ArcGIS Online in a frequency, like every 3 minutes that map gets updated. S3 is getting updated, and the map is getting updated in real time. So, and that same stream is also feeding our backend and voice assistant from Alexa. There's a skill, I'll show it in the next slide. So below is the StormSense HIST, where we are collecting data 7-day, 15-day, 20-day. We can expand the way as we get funding, we'll expand to 30 days and then go to the next step. So that's the StormSense HIST, and that has a gateway API we are using to bring that data out. So here's our Alexa skill, which is on Amazon skills on Amazon.com, and the citizens can ask StormSense, what is the water level, what is the wind speed. They can ask their neighborhood. They get the real-time data. And if it's a NOVA station or if it's a USGS station, whatever they are reporting at whatever their frequency will be showing, that will come out as voice. And what happens is every data which comes out of that voice interaction, it will also tell what is the data source. So that's very key for federal agencies for us to do that. And in the future, we are going to have the chatbots. So that's the mainstream which goes to the citizens, so they can type in Skype or anywhere else and get data wherever they are. And then we are also building an iOS, Android, like a React.js app for that, also for the citizens to use. We're going to use EcoSpot and EcoShow to show the charting data in real time. Whenever the charts are up, they can see the charts. So the predictive tools and multi-cloud environment, I've just gone through that part. So IoT data to support model results in real time, and we are using hydrodynamic and then predictive charting from the hydrodynamic modeling as well. And then hindcasting is like previous storms. We did some simulations of those storms to show. And then also we are using these three, AWS, Esri, and Microsoft for mapping and visualization, as well as the real-time data streaming from AWS. And we are doing a lot of different prototyping that side, and citizen awareness through voice. And then the machine learning is the next step we are going to go through. So this is a sensor asset map. So here are the sensor and the sensor picture. And this is a real-time map. So you see the points which shows water levels, wind speed, and everything, what direction the wind is coming. Left side is an Alexa for them to know which bridge they want to call. So things like that, we are adding more knowledge to Alexa there. And here is visualizing water level data for on the scientific community, as well as city officials, as well as public. They can click on anything on a different data set. StormSense is one data set, USGS is one data set. They can compare two different sensors, and they are also able to do precipitation. They can see different precipitations at different sensors. Sometimes the sensors are not right. So here we have created another visualization tool called outliers. One sensor will be beside the other, and one will be saying 0.1 inches of rain, and one will be saying 1.5 inches of rain. We want to see that. Is the sensor doing something? So that's the machine learning part we were going to see how we can leverage that. And this is our planning for the future. So here we are putting a deep lens camera on a bridge, and then also deep lens camera on some intersections. So what we are going to use is we will be taking the sensors data and actually taking photographs, pictures of the rivers. Most of our bridges are lower, so we get a good picture of the river as well as the banks. And we want to see the rise and fall depending on different patterns of rainfall, which goes over a period of time. So what is happening in our community is when we are from one event to the other, we completely forget about the previous event because we can't see that in a long period. So that's what we are trying to convey here in the future, that how we can keep that memory as we go along in 5 years period, because sea level rise is going to be a long-term thing. So we want to understand the whole system of water, how it's flowing within our city. That's why we are densifying to that 35 to 50 sensors across the city. So here, serverless photo recognition, frame-based analysis. This is already there on AWS website, so we can use that. I think the deep lens camera, I think I got last week in mail, so I'll be using that to do some testing on that and prototyping. So our next step is the history, the data history. We'll be pushing it to Athena and then the Amazon Redshift to do the analytics in the future. So that's our project. If you have any questions, and you can come over.
Hi, if anybody has any questions, you can just put your hand up and we'll bring your microphone. Anyone? This is one over here.
Thanks for the presentation. So I wonder about the cost, the relative cost of doing the remote sensing, especially in poor countries, compared to the actual activity. So how much does it cost to put the sensors there with Wi-Fi or like with internet connectivity versus the whatever they use to cook in?
Yeah, it's a good question. So if you look at a standard clinic in Mozambique, the annual cost of the vaccines stored in that clinic, usually it's about $10,000 worth of vaccines. And now that doesn't even include the cost of repeat visits, getting sick, cost of life, et cetera, just the actual hard vaccine cost. It doesn't include the cost of the fridge or even the cost of transporting the vaccines, all of which adds quite a bit more. But if you take $11,000, let's call it $10,000 a year as the cost of the vaccine product in a standard clinic, the cost of the monitoring in a study that was done in Mozambique ends up being about $100 a year, sorry. So 1/10 of the total cost. And so you think of it a little bit like insurance. Yeah, for the cook stove, so that's partly why we've really shrunk down the sensor, because the picture you saw there, it was like the cost of the device ends up being like 5x the cost of the stove. It's something just totally ridiculous. The current technology we have is still not where we'd like it to be. It's like 50% the cost of the stove. So cost reduction is a big issue, but not my top priority, only because we just don't have anywhere near the types of economies of scale that we could have. So in terms of the cooking, you're talking about roughly 600 million households. And as you start building these sensors into the cook stoves themselves, then you start leveraging massive reductions in cost. And so you could get down to a couple dollars. It wouldn't be GSM networks, it would be Bluetooth, but then Bluetooth to a cell phone that hops it up to the network. So, so definitely an issue, not necessarily the number one priority as we kind of work to build out the broader market and use case.
Do you really need to track every stove? Can't you do statistically modeling to cut down the 50% cost to 5% or something, like only tracking 1 in 10 of your 600 million?
Yeah, but so it really depends ultimately on the use case and what we're talking about. So for example, what we're doing with the World Bank, where they want to do results-based financing, where the World Bank only wants to pay a stove manufacturer if they actually deliver a stove that women love and actually reduces pollution. Then absolutely, you could do subsampling. You could go down to, sample sizes, as you're saying, 1 in 50, 1 in 100, probably fine at some level of scale. So it really depends on the use case. For another use case where women are actually getting high quality verified climate credit payments for their usage, subsampling doesn't work because there is still quite a bit of variability in the usage. But absolutely, all sorts of things that we're considering in order to bring down the cost. Like I said, cost is just not really the big concern right now. I think there's such a big potential upside. I mean, if you look at every dollar spent in the development sector right now, I mean, very little of it is actually making any actual impact. And so I think across the development sector, when you talk to any of the big sort of players, the World Bank, et cetera, they're not as cost sensitive as you might think in certain ways because they're just trying to get to impact. And so, then we can start talking about it. Once you get to something that works, which is so rare, then we can start talking about how do you make it more efficient, how do you get economies of scale, how do you get efficiency, how do you get other manufacturers to come in and compete and bring down the cost.
Hi, my name is Brandon. I'm with OpenStorm.org. I have a question for StormSense. I was wondering, so you're planning to scale up. How do you decide, you showed pictures of like various places where you deploy. How do you decide where to deploy and like what factors play into those future deployments?
Oh yeah, so there are 2-3 things which are happening currently. I think one is the USGS network of stream gauging, and there is the other one called National Water Model, which predicts the volume of water which is flowing. And in our case in the city, what we did was we pre-modeled some of the storms before in the hydrodynamic modeling process, and with that we came out with the sensor locations. And we also took the input from the city engineers, what is happening around the surrounding areas and what has flooded before as intersections. So that's the building block we are using currently to do that. So if you do a next step of another area, so we got calls from North Carolina to do their sensor network. So they were asking, the first 2 questions they asked was, what is the cost and what type of sensors you're using? So we are seeing that a lot more interest is in that phase of, because this study will give them a quick way of a number and then how fast they can acquire some of these things to start off. That's how we are looking at that. And they will be doing, with their knowledge also, they'll be looking at their network of and then giving us some information about their future. And then at the same time, we model that area.
You said you're sending your StormSense data straight into ArcGIS Online.
Mm-hmm.
How are you doing that? With a REST URL, or is there something fancier behind it?
So in ArcGIS Online, what happens is we send the data in 6-minute intervals, the data. So we have lambdas which will every 4 minutes they run, and then they bring the data into this location of S3 as a CSV file. So in ArcGIS Online, what you have is when you add a map, you can add a layer as a web layer or as a file. So what you do is you choose the web layer, and when you have a web layer, what it does is it lets you give a URL way of connecting to the CSV. So when the URL is connected to the CSV at the back end is running constantly every 5 minutes. And in ArcGIS Online, you have another place. When you add the layer, there is a place where it says, can you set the time frequency? And there you say, okay, 4 minutes, I want the time frequency. So when the S3 is running in the frequency, this is running in the frequency, and you can see live on the map that the data is changing. So that's one option I used. And there is another open source called Coop, K-O-O-P. Check that, and what that does is you can do the S3, take the S3, and then you can convert completely into in a timer in Lambda, you can make it convert it into a Esri feature layer directly, and that can be another way of doing a real time. Did that answer your question?
Yes, thank you.
Sure.
others? All right, thank you guys once again. Really appreciate you guys.
Thank you.
Thanks, everyone. That brings the formal agenda to a close for today. Please, we hope you'll join us for the party upstairs. Kicks off at 4 o'clock. Have a drink, have a dance, and enjoy some 80s music, I think. Who doesn't love some 80s?